Good morning. Welcome to Survey Research Methods. I'm going to be talking to you today. My name is Rodney Sparapani. I'm in the Division of Biostatistics. I'm an assistant professor, and I've been working on causal inference for the last 15 years, but I do not really consider myself an expert. It's a big field. It's an evolving field, and I feel it's a very important field. I don't know if one lecture can do it justice, but I'm going to try. So why don't we go around the room and you can tell me about tell me your names and your background, what you're studying, etc.
So my name is Ben. I'm a part-time second-year public and community health student. I work as a chiropractor with Aurora in Sheboygan, so come up here a couple days a week for school. I'm interested in spinal health, and right now working on a project with the lung population in Sheboygan.
Okay.
My name is Jared, also in the public health program. I'm interested in a lot of neighborhood effects and place-based interventions, and so I'm really interested to see this. I've been looking at different approaches to natural experiments, and then also some opportunities for different approaches that like quasi-randomized that we're in the reading. So I'm really intrigued to see different paths.
I'm Bennett. I'm a second year in the public health education program, and the research that I'm involved in looks at development of PTSD and trauma survivors.
Okay.
I'm Ben, second year too. I am interested in the relationship between precarious work and health.
What's that?
Precarious employment and health.
Oh, okay.
I'm Terrette Jackson. I'm a second year T32 postdoctoral fellow, and I'm interested in not only socioeconomic factors but also health system factors that impact diabetes self-management as well as diabetes care outcomes.
Okay, so we're recording this today for the Biostatistics lecture series. So let's get started. By the way, if you have any questions as we go along, I think it's very important that you ask them because I'm just going to blow through this if nobody stops me. Okay? So even though this is being recorded, we've got an hour and a half. I think we're pretty safe. All right. So for those watching at home, there was an assigned reading, which we'll see at the end of the slides. So this is your chance to stop watching, go and read these two papers first, and then come back and watch the rest of this lecture. All right, so did everybody have a chance to read these articles? I think they're two very good articles, and they're written at a fairly low level, very understandable, which is unusual in the causal inference literature. Usually there's a really complicated series of formulas and theory, references to papers that aren't easy for us to obtain in either econometrics or some other obscure journal. So these two articles are actually a treat. And there are some other good articles. We'll see them at the end, and you might want to dig into those too. But I find that these two articles are probably two of the best. All right. So the reason causal inference is important, I think, is because comparative effectiveness research is important. Okay. I'm going to talk about some unpublished work, an example from a study that we did on breast cancer surgery. I'm going to talk about potential outcomes, propensity scores, instrumental variables. We're going to return to the example. I'm going to show you some SAS code on how to do it, how to do propensity scores and instrumental variables. And then we're going to talk about near-far matching. Okay? I looked around, actually couldn't find a definition of comparative effectiveness research that I liked, so I made it my own. So this is what I mean when I say comparative effectiveness research. A fair comparison of 2 or more active treatments in typical community healthcare settings among a generalizable population of health facilities, caregivers, and patients. Okay, so well, let's continue. So CER is often carried out by randomized controlled trials or via observational data. The pros are, obviously, randomized trials are the gold standard, right? They're the best. Randomization will balance risk factors between the 2 or more treatment arms, and you just don't have to worry about them. It's causal. It's causal inference, and that's been known for quite a while. However, there's a downside to RCTs. They're costly to carry out, and industry rarely does the type of randomized controlled trials that we would want to see. Usually the FDA only requires that a new treatment is better than current care. It does not require people to, it does not require companies to compare with a competitor. So, so there's a big lost opportunity, I feel, but I can sort of understand why the rules are the way they are. So that means that if we want some sort of evidence about 2 treatments, we have to run our own trial. You're not going to find that trial generally in the literature or provided by the industry. So that means you need money. Okay, well, what about if you're like me and you don't have any money? Then we're going to look at observational data. Okay, the pros are there's large data banks, readily available, cheaply available. I mean, cheap is all relative, right? I mean, far less than it would cost to run a trial. Let's put it that way. The bad news is the risk factors are probably not going to be balanced. And you know, if you don't believe me, we'll see why that's true in a minute. And so therefore, we need some sort of causal inference techniques to deal with this and with observational data. Okay, so let's look at a randomized trial. So like we've been saying, a randomized trial is sort of the best situation and what we want to emulate. So we have our risk factors here, X. We have our instrument Z, which could be the randomization. We have our treatment T and our outcome Y. So in causal inference, this is what's known as a causal path diagram, because if you look at these arrows, oops. So if you look at these arrows, they indicate causality, but they don't necessarily. I mean, these are the arrows we're going to estimate. So, for example, we're going to estimate what is the relationship between T and Y. Now, there may be no relationship, right? But we're allowing the possibility that there is. So if we had no arrow here, then we would say, well, Y and T are just totally independent, which would be kind of a boring trial. But anyways, so notice the risk factors have a bearing on the outcome. The treatment has a bearing on the, the randomization has a bearing on the outcome only through the treatment. See, there's no direct path from Z to Y. All right, so that's a randomized trial. Okay, so what happens in observational data? Well, notice we have this additional. Notice we have this additional arrow here. There's an arrow that goes from the risk factors, which are now called confounders because they're confounding the treatment. There's an arrow that goes directly to the treatment. So so for example, if you have a patient who you know is at higher risk for an outcome, you may be more willing to consider more advanced treatments or more, how should I say, more complicated surgeries or more medications that possibly have more serious side effects, right? So that comes into the mix. And notice that everything else is the same. So the only thing that has changed is how X operates. Okay? Any questions? All right. I love this slide. I put this in all my grants. This is a great slide. Okay, so let's look at an example. First, let me tell you about axillary lymph node dissection. So, let's say a woman has breast cancer here in her left breast. So they remove the tumor in the breast, but they don't know where how far the cancer cells have gotten out of the breast. Okay, so generally the cancer cells follow the drainage system in our body, the lymph node system. So these lymph nodes, they store fluids and then they pass it on these lymph node channels, and they drain. So the breast drains this way, and the arm drains this way. Okay. So the worry is that that the cancer cells have gotten out to some of these lymph nodes. Okay. Now notice this lymph node here is marked SLN, the sentinel lymph node. So this is the first lymph node in the chain up from the tumor. Okay, well these aren't labeled in the body. These are really tiny. They can't even see them. Okay, until they open you up. So generally, what the practice has been in the past. Well, I think I have that's on the next slide here. So in the past, let's say prior to 2000, they would just take a biopsy somewhere in the armpit. They call it axillary lymph node dissection, and they would get several nodes, maybe 4 or 5 nodes, and they would check them all to see if they have cancerous cells in them. Okay. So I don't know the exact year, but around 2000, they said, well, wait a minute, let's inject a dye into the tumor, and we'll watch to see which of these cells gets the green dye, or which of these nodes. They find this node with green dye in it, and they take it out. Okay, and there may be several nodes that are really close together, maybe 2 to 3 nodes, and they take those, and then they check those for cancer cells. Well, so why bother? Well, the problem is, like I said, these nodes drain your arm. So if you take too many cells just by taking a dissection of this area, you may obstruct the channels in the arm, and people get what's called lymphedema. Their arm swells up, and it's like one of the things that breast cancer survivors complain about the most. And then there's really no treatment. I mean, they can wear these bandages that try to force the edema, but it can be painful and itchy, and it's just a weird feeling, I guess. And like I said, it's as far as quality of life is concerned, it's like one of the biggest factors for breast cancer survivors. Okay, so there's two treatments: axillary lymph node dissection and sentinel lymph node biopsy. Okay, and of course we want to know which of them is better, which is going to have the least side effects. So we had this study, outcomes of older women with early stage breast cancer. We spent a long time coming up with that catchy name of the study, and that's the best we could come up with. But I don't know. It got funded and we got it published. Anyway, so what we did was we took out all of Medicare claims in 4 big states. And what we wanted to do was we wanted to find breast cancer patients who were operated on in 2003. You know, Medicare doesn't actually tell you who's a breast cancer patient and who's not, unfortunately. That would be great, but they don't do that. So we actually had an algorithm that we had worked on a couple of years prior to that helped us where we were able to validate it and show that we could reliably identify who is a breast cancer patient and who is not, just from their claims. Also, we needed, or we wanted to identify the hospital they were treated at and the surgeon that operated on them. However, there's a big sea change in the 90s where only about half of the women are actually treated in a hospital. Some of these women are just having outpatient mastectomy. That kind of caught us a little bit off guard. We knew it was happening, but we didn't think it was about half of the patients. But it's about half of the patients. And quite frankly, today, it's probably less than half are treated in a hospital. Maybe only 30–40%. So it's so identifying hospital is a challenge, but we're gonna live with that. All right. So we had their claims. We contacted them on the phone. Well, first we had to find them, but we have a service. We used the survey center at Madison to call these women. We asked them questions. You know, did you have breast cancer? You know, yes, no. All kinds of questions about their treatment, and you know, other things about their quality of life, etc. So let's see. We had about 3,083 in wave 1, and 2,788 in wave 2, where we talked about their lymphedema status. And that was about 3 years of follow-up. So this is about 2006. Okay. So we had, we said we had 1,738 women, mainly because of the problem I was talking about, where only about half have a hospital that they were treated at. Some about half are going directly to the clinic. So, I could have done this on the bigger population, but I didn't. Anyways, so axillary lymph node dissection was still being performed. Some people think that it's better for certain women, you know. So what happens is some women have what's called a palpable node, so they can actually feel the node that may be involved with cancer. They can feel like a solid node. And some people say, well, okay, in that case, then we're going to do axillary lymph node dissection. Whether that's really needed or not, who knows, right? But, and then some people are just not trained on SLNB. They don't have the technology, like they don't have access to the dyes, because all of this has to be orchestrated in the operating room. You know, they take it out, they freeze it, they slice it up, and they send it to the pathology lab, and you know, it's a big operation to do this quickly and do this well. So some surgeons don't have the training, or their hospital doesn't have, or their clinic operating room doesn't have the capabilities, whatever. But even in 2003, you can see that more people are getting SLNB than ALND. And today, that's probably even more the case. So there was a randomized controlled trial that showed that SLMB reduces lymphedema rates, which is an adverse outcome, of course. So why do we do this study? Right? We already have a randomized control trial. Well, okay. So the trial, they really wanted to show a difference, right? So they had people who were like experts in SLMB, and they only picked certain centers that were really well known for it, and blah blah blah. So they narrowed the field, but obviously, very few women are being treated in those particular centers. There's lots of these centers all over the country, so we wanted to be able to generalize this in what we call community care. So does SLMB reduce lymphedema rates in community care? Well, okay, so let's look at our survey. First of all, notice so there's a pretty big difference, about a 10% difference between the two arms. Okay, but there are some differences. Okay, age. The women in the ALND arm were a little bit older, not huge differences here, but it was significant. Significant difference. All of these are significant, but you can see it was not really a borderline case. There's a thing called the NCI comorbidity index, and so what it does is it looks for certain diagnoses of the claims of breast cancer. It does it for all of the major cancers. There's one for breast cancer, there's one for prostate cancer, there's one for lung cancer, and there's one for colorectal cancer. So basically what you get is a range. I forget what the range. It's like 0 to 11 or something. But we normally break it up into what we call 0, 1, or 2. Okay, so just averaging these over the two arms, you can see that the ALND group has higher comorbidities. And this is even a more significant difference than age. Okay, so that's related to the patients. What about to the treatment? So this ASBS, what that means is, did the surgeon who operated on a particular patient belong to the the American Society of Breast Surgeons? Now this group obviously has a lot of specialization in breast surgery and would be way more likely to provide SLMB, right? And you can see, look at that. You're almost never going to see a Z that big.
So 34% of the SLMDs.
Yeah.
16%.
Right. Exactly. Look at that. A minus 8.2. That's like something you could hope for in your dreams, right? But in this case, it's all related to the treatment, so it's not it's not pertinent, let's say. But just to show you, you have some major differences here. That are dictating whether the surgeons are giving the patients ALND versus SLN. And if there's a randomized trial, those differences they would be gone. There would be no differences. All right, so let's talk about what I call the causal treatment effect, and then what is known as the counterfactual. Okay, so here I'm going to talk about a binary instrument. So Z is binary, and T is binary. Although T doesn't appear here, but I mean basically, when you do a randomized trial, you usually analyze it intent to treat. So that's Z. So generally, you randomize somebody to treatment. Usually they get it, and occasionally they don't for whatever reasons. Okay, so this is just linear regression. So we have an outcome, we have some intercept, we have this beta that's associated with the treatment, and then we have these risk factors. Okay. Well, you know, if you have a certain type of trial, maybe you can give the patient both drugs. Like, for example, if it's an asthma trial, you give them a drug for, I don't know, a couple months, you have a washout period in between, and then you give them the other drug. Well, the type of studies I'm talking about aren't like that. Usually these are mortality studies, or they're acute MI studies. So you really only get one crack at it. So you can only give them one treatment at a time. So I use this plus. I don't know if this is great notation, but I kind of like this notation. Use the plus for the treated patients and the minus for the untreated. So now notice these two error terms are not the same, but the rest of the parameters are the same. Well, okay, so if we wanted to know the causal treatment effect, all we have to do is take the treated value you would have gotten if they were treated and subtract off the value from the untreated, and then just take the average over the population and you'd be done, right? Well, we can't do that, right? That's the whole problem. We can't give the patient both treatments. Well, in a randomized trial, because it's randomized and there's no confounding, you can do this. So you can take the average of the Y's from the treated group and you subtract off the Y's from the untreated group. You get this, these things cancel, voila. So something like that is what we want to be able to do in causal inference. So we want to be able to do this, but we can't do it like that, so we have to figure out some other way to do that. Some other way to do this, right? Okay, so biostatistics had generally ignored this until the early 80s. So that's when, well, first of all, comparative effectiveness research started to get going around that time. It was a very popular topic, even possibly more popular than it is today, if that's even believable. And but they realized right away that, wait a minute, this doesn't make sense. You can't do this all the time. There's certain treatments where the physician obviously knows something's going on and is changing the treatment based on the patient's characteristics. So Rosenbaum and Rubin started the propensity score. Okay, so if we knew all of the confounders, then we can take advantage of what's called propensity scores. So we figure out this probability, this function of the x's that's called the propensity score. It's the probability of being treated given those confounders. Okay. So for example, and in this case, we're talking about a binary treatment. Okay. For example, if you do this via logistic regression, you get this. You're estimating these parameters, and then it seems to work pretty well. Okay. So then we can use these probabilities to adjust our CAR analysis. So the pros and cons. This is really easy to do, right? You can do logistic regression. You can do this. The bad news is, if unmeasured confounders exist, the method is no longer applicable. So if there's some x's that we don't have, we're in trouble. And remember now, this is observational data, so you may or may not have all the x's, right? Another con, this came up for us. It's not always a problem, but it doesn't work very well for multiple treatments either. So you get in a situation where you can't compare them all at once. You have to compare them head to head, like a round robin or something, which kind of gets to be painful. Then there's a few different methods: stratification, regression, matching, and weighting. Okay, weighting is a little bit more involved, and we're not going to talk about it today, but just so you know that it exists. All right, so let's talk about stratification. It's also known as subclassification, and it's very similar to regression, quite frankly. So they're not identical, but as you'll see, they're pretty similar. Again, the pro here is it's very easy. The con, the statistical treatment, statistical test of the treatment may not be obvious, or maybe obvious is not the word. Maybe it. What would be the word here? Maybe it's not convincing. Let's put it that way. And we'll see in a minute what I mean by that. All right, so so matching is really popular. A lot of studies on matching. I think matching's it's a pretty good approach. Definitely D'Agostino likes matching. It has some things going for it. So it's really good for cases where you have relatively few treated patients and a large number of untreated patients. That way, it's very easy to find a good match for each one of your treated patients. However, the con there is if you have a roughly equal number of treated and untreated patients, then the matching is more tricky. And what happens in matching, if you don't match somebody, they're lost to you. So, so that's a downside. One of the pros is it requires a matched analysis. And generally, matched analysis are more powerful. So it really, like I said, matching is a really good idea. The problem is sometimes people feel the matched analysis is more difficult to interpret, or they just simply forget. Somebody looked at the literature. Austin looked at the literature, and I think he looked at like 70 papers, and he found like only 10 of them did the appropriate analysis. So people either don't want to or just forget to do matching, and so it's kind of I don't know. It's not the way you should do it if you get the chance. Okay. So now I'm going to show you how this works in SAS. So let's see here. So D'Agostino showed some code. Why is this so small? This is not going to be good. Let's see. So D'Agostino showed us some code, and I'm going to, I'm going to try to show you some code here to do propensity score analysis. How many people are SAS users? Oh, good. Oops, I logged into the wrong server. I love these live demos. All right. That's better. Okay, so how does that look? Is that legible? Huh? Oh, is it on the side?
Yeah.
Oh, wait. How's that? Is it better?
Yeah.
Okay, so I'm not going to go through all of this. So the first part of the code is just setting up the data. Okay. So so the idea here. So this is the breast cancer example I was talking about. So what we want to do is we want to predict who gets SLMB. So there's a few things. As we saw, age is different. Okay. NCI, that's the comorbidity index, is different. Also, I'm going to use what we call hospital score. So one thing I forgot to tell you is not only did we have all of the claims for the breast cancer patients in those 4 states, we had all of the claims for everybody in those 4 states. So we could look at a hospital and say, okay, what kind of specialized cancer care did they offer? I don't remember what they all were, but SLNB was one of them. You know, I think chemotherapy was one. There's a type of radiotherapy. So there's like 5 or 6 things. I think 5 things. So the hospital score was 0 to 5. And it was some sort of a rough measure of how specialized that hospital was to cancer care. And we had hospitals all over the spectrum from 0 to 5. And then we had surgeon volume. So like I said, we had the claims for everybody. So we could see for each patient surgeon how many breast cancer patients they had operated on. Okay. We also had their surgeon proportion, so we could see. Sorry, I'm not going to explain this right. Their breast cancer proportion. So some surgeons had a higher proportion of breast cancer patients than others. So some surgeons were really specializing in breast cancer, and some surgeons were just doing it on the side. So we had everything from 0 to about 66.6%. So one surgeon had 3 patients, and 2 of them were breast cancer. But I mean, generally the high surgeon proportion patients or surgeon proportion surgeons were not low volume. Only one of them was really high. The rest generally were high volume surgeons. So that sort of makes sense. High volume surgeons, you know, I mean, this is how they make their living. They do a lot of these. They may do several women a week. Okay, what else? Oh, and the membership in the American Society of Breast Surgeons. Okay, so here's something that sometimes people forget, and actually I forgot when I first did this, was one of the things about the propensity score model is you don't really care about this model, right? So the idea here is you put in everything you think might work, whether it's significant or not. Okay? Does that make sense? Because all you care about is predicting who gets what. You don't want to interpret the model. The model's a throwaway model. So also I included all 2-way interactions. I'm not going to try to interpret those. I don't even know if they're significant. I know it did improve the fit. The fit got a little bit better when I added them, so I threw them in. Some people go further, like if they have continuous variables, they add the squares, they add the, you know, blah, blah, blah. Let's see, I don't have any continuous variables, so, or, wait, do I? I do, I have surgeon proportions, so I could add surgeon proportion squared, but I mean, this is just for you guys, right? This was never published, so I had freedom. Okay. All right, so, okay, so this is just looking over the code. Like I said, really we're not going to say too much about it, I don't know, unless anybody's curious. What I like to look at here is I like to look at the C index. Okay, so a model that's a nothing model is, I think, a C index of 0.5. So this is you know, about midway between 0.5 and 1, which is the maximum. So a decent model, nothing to sneeze at. A lot of biostatistical models are in this range. I'd say anything above 0.7 is probably pretty good. So we got a decent model here. All right, what's next? So, okay. So the way common practice is to divide it into five groups, the quantiles. Why 5? Well, it all comes down to a paper many years ago about somebody talking about how do you divide up something and still salvage the power and etc. So 5 groups, but there's nothing magic about 5. You know, could be 10, could be 7, who knows? But just about everybody uses 5. Okay, so that's all I'm doing here. I'm just making 5 groups. I'm creating this variable strata. All right, let's see what happens. Do these strata balance our treatments? All right, let's take a look. But I shouldn't say balance. What do I want to say here? This is what I want to say. Okay, so 0 are the people. 0 is the group with the lowest. They have the lowest probability of receiving SLNB. Okay, and what you want to see in this group is that there is a substantial number in both. They call that overlap. So let's say there was everybody got ALND and nobody got SLNB. That's an overlap. That's not good. So then, if that was the case, you would eliminate this strata from the analysis, okay? Or the other way. So here I saw a lot of overlap. I didn't really see a problem. You know what I mean? Everybody get that?
Even with that last category, number 4.
Yeah, it's not terrible.
Disproportionate.
It's disproportionate. Well, they are going to be disproportionate. Okay, so let's look at that. So in the group with the lowest probability of receiving SLNB, you'll see there are more ALNDs than SLNBs. And as you go, you'll see it goes the other way. When you get to the group that has the highest probability of receiving SLNB, there's more SLNB than, I mean, that's what probability means.
Yeah, so it's more like if you have a small numbers problem.
Right. So if you get if this is like 0 or 1, and you know, then you're in trouble. Then you just eliminate that. So usually, then the cutoff is here, and you use 4 instead of 5. I mean, but it's no big deal. But here's the point, though. So this strata is balanced on all those confounders. This strata is balanced relatively, way more so than the study at large, right? Because that's what we did. We made these by confounding groups. Okay? All right. So now we've got to come up with a statistical test of this. So it's kind of obvious in this case. Sometimes it's not. Anybody see it? Anybody know what the test is going to be? Huh? No? Okay, that's one approach. I was thinking something similar, simpler. I'm going to do proclogistic too, just to show you. Well, what I saw was this is a Mantel-Haenszel test, right? We have five strata, and so let's take a look at this. So the way SAS does it is they do each of these one at a time. So you can see. So here on the columns, I've got lymphedema, yes or no, yes, and SLNB, no, yes. Okay, so this is for the 0th strata, and you can see, so those are the numbers, and you can see for this strata, what happens? Mantel-Haenszel test, 5, pretty strong, significant effect just in that strata. Okay. All right, and you can go to the next strata. Okay. What do we got here? It's even more significant in the first strata, etc. I'm not going to do every one of these. Well, let's see. I want to find one. Okay, here, the 3rd strata. You can see, interestingly, not significant in the 3rd strata. I don't know what's going on there. 4th strata is significant, and then the 5th strata is significant. So then you put all of those together, and there's an overall test called the Cochrane-Mantel-Haenszel test. Okay, and you can see, you put all those together, it's wildly significant, right? Because 4 out of 5 were significant, so you know what's going to happen. Also, let's see here. So this, I'm trying to remember here. So, okay, so it also gives you a relative risk. So in this case, this is a cohort study, right? Because we have everybody. We don't just have cases and matched controls. We have everybody. So you can go down here, and so lymphedema was the second column. So this is what you look at. So you can see that the rate, the relative risk, there's twice as much lymphedema overall in the ALMD group than there is amongst the SLM, which is what we would expect to see something like that. And with a very significant p-value. You know, you can also see the range here. Well, I mean, this is great, right? This is like an awesome study. So why is this unpublished research?
Such a limited list of confounders.
Yeah. Because there could be something out there that we just don't have. Because when you get the claims, there's lots of things you don't have. You know, you don't have, I don't know, you don't have blood pressure, for example. You know, there's all kinds of things we don't have, you know, that you would have if you had an EHR data maybe, or something. I don't know. So there's all kinds of things we don't have. So it's back to the drawing board, right? All right, so what will we do now? We would do instrumental variables. All right, so back to the causal path diagram. So, oops. Well, yeah, that's right. All right, so I talked about, in a randomized trial, I talked about Z. That's just the randomization, right? What I didn't talk about was over here. What the heck is this? Right? There's no randomization, so it can't be randomization, right? But I mean, it's filling the same capacity. We call it an instrument. And this instrumental variables approach, the pro of instrumental variables is the method is still applicable in the presence of unmeasured confounders. So the econometricians were hip to this way before the biostatisticians. They've been doing something like instrumental variables since the 20s or 30s. So they had us by a long shot. And I think part of that was just the nature of economics. You can't easily control stuff, so they knew they needed this. Whereas like in agriculture, you can move one plant to a different field or something. In agriculture, where biostatistics came from, we didn't have these kind of problems. At least we didn't think we did, but we do. All right, so what's the bad news? Well, the identification of a suitable instrument is often challenging. It's just tough. You need to find something that predicts the treatment without predicting the outcome. Notice there's no arrow going from Z to Y. The only arrow is through the treatment. So it predicts the treatment, but it does not predict the outcome. In fact, that's, well, okay. The good news is the outcome can be either binary or continuous. And so can the treatment. However, with the first approach, what we call two-stage least squares, the binary outcomes can't be near the boundary. So they can't be either really small or really big. All right, but let's address the first con first. What are some instruments that are used in the literature? Well, generally they come from natural experiments. These are mainly mortality studies. And like I said, in mortality studies, you just don't get another chance. You can't assign the treatment to both, you know, you can't assign the same patient twice because they may be dead. So this is you know, this is where you see them the most in the literature. You see them in mortality studies. Okay, so there's a famous study, and actually has 2 publications. They looked at coronary procedures. So they looked at distance to the hospital. So, you know, when you have an acute coronary event, you get in the ambulance, they take you to the closest hospital, generally. So that's a good randomization factor. Now you have to buy that people don't live closer to a hospital or something. You know what I mean? There's not something about the geography that where the healthier patients live closer to the hospital versus further away. But I think we all buy that, right? I mean, they got 2 big publications. One is in JAMA, so I mean, it was a pretty big deal. So distance to the hospital, the treatment is coronary procedure. Which coronary procedure they got when they got to the hospital? I think they were. Some people didn't get cath, and some people got cath. Of course, this was kind of old data. Nowadays, I think almost everybody gets cath, generally. I could be wrong about that. I know in the 90s there's a lot of big ramp up on cathing. So, okay. Angrist has a famous paper. The instrument is the Vietnam Draft Lottery, and the treatment is military service. And like I said, the outcome in all of these is mortality. Okay. Gewicke, I'm not sure if I'm pronouncing that correct. He's Dutch, but he had a similar one. It was distance to hospital. I mean, he had the same instrument, distance to hospital, but the treatment was hospital quality. I don't remember the particulars of that study, but that's a famous study. And then Baiocchi, this is the other paper, right? The near-far matching. So their instrument is geographic region, and again, the treatment's coronary procedure. Okay? Oh, that was weird. Okay, so way back in the 50s, Thiel formalized this technique. Essentially, it's a structural equation model, but he's solving it with 2-stage least squares. So what do we mean by that? So we just have stage 1. He does a linear model here. Now, even if t is binary, he's doing a linear model. Okay, like that. So he has the instruments and the confounders in the first stage. And in the second stage, again, he's allowing y to be either continuous or binary. And like I said, but it can't be too close to the boundary if it's binary. It has to be some distance away from the boundary, like between, say, 15 and 85% or something like that. Okay? You know what I mean? But now, notice what he does with the treatment. He doesn't actually use the treatment, the real treatment. He puts in t hat from the first equation, from the first stage. Well, what the heck does that do, right? I mean, it sounds good at first, but then you're like, wow, what does that mean? Well, it turns out, well, this is just saying what t hat is. So t hat is just this, right? There's no epsilon in it. It's just this. But we've got to make it. We have a few assumptions we need to make. First of all, we assume the errors are 0. Okay, we always do that. So what, right? But okay, here's the big one. We assume this epsilon and t hat are uncorrelated. And similarly, this epsilon and t hat are uncorrelated. Okay? Okay, if you buy that, and these two are non-zero, see, this one can't be 0 because this turns out going to be on the bottom. So it turns out this beta, what is it? They call it beta hat IVE, the instrumental variable estimator. But it's the variance of y and t hat over the variance of t and t hat. And that turns out to be the causal parameter that we were talking about before, beta. So that's the causal effect. So smart use of linear regression here. I would almost say an omniscient use of linear regression, and it works. And they've known about this for, since the 50s. All right, so I'm just going to go through this quickly. So why does this work? Well, first of all, notice, okay, so if we assume ordinary least squares, and by that I mean, what do I mean by that? By ordinary least squares, I mean, suppose there was no stage 1, and you just took stage 2 and you plugged in the real treatment, okay? So that's it. There's no 2 stage, so just 1 stage least squares, okay? So then your x would look like this, right? You'd have a vector for the intercept, you'd have t and x, right? Because that's what you're going to use. All right, well, like I said, one of the keys to notice here is this proof doesn't assume any distributions. Like, what do we always assume in linear regression? Normal errors, usually, right? Nothing in this proof uses that. This is a distribution-free proof. And what is this proving? It's proving that just using stage 2 alone doesn't work. Let's see. So this is the normal beta hat estimator, right? Let's see here. Okay, so what is x prime y? Well, it turns out it's this. Okay, and what is this thing? It's that. So what we're showing here is x prime, which is this, times epsilon. And remember, there's only 1 stage, so there's only 1 epsilon here. If you divide that by n, as the limit goes to infinity, this does not go to 0. If that doesn't go to 0, then this is not 0, which is one of the assumptions, right? Let's see. Yeah. See, we needed that here. So what does that mean? Okay, so generally what that means is when we collect more data on something, generally more data is better, right? In this case, it's not. More data doesn't help you at all. So what do we have to do? Well, it turns out we have to do 2-stage least squares. And the way you do that is, instead of putting x prime in here, we put z in here. And now z, notice, doesn't have t in it. And that's the key. So just jump down to the end, you can see this. Z prime times epsilon. Divide that by n. As n goes to infinity, this goes to 0. If that goes to 0, then our beta hat IVE goes to beta, which is the causal effect. It's beautiful, right? But notice, no distribution here. Not assuming anything about distribution. So that's why IVE works. What else? Okay, so that's theoretically, but in practice, what you need a strong instrument treatment relationship. Okay, and we'll see that later on when we talk about Bioki. So Steiger and Stock show that partial F test of 10 is needed to be a strong instrument. And then Conley came up with some ranges of R squared. So you can see strong instruments are in this range, 0.6 and above. Okay, so so there's this thing I call the non-parametric axiom of causal inference. So it says, causal inference of an observational study requires the non-parametric identification of treatment effects without relying on functional form restrictions or distributional assumptions. So I'm going to ignore this part first, for now, or I guess in this whole talk, but notice distributional assumptions. You can't rely on a normal distribution or something like that. Because what's going to happen, you'll send in your paper, the reviewer will say, well, you assume normality. That's it. You're done. You can't make those assumptions. So that's why instrumental variables is neat. Because it gets around the distributional part. The functional form thing is more complex, and I think that's where the modern research is all about, the functional form. But they did this right. They had that figured out. All right, so let's go back to our study. Just to remind you, we had California, Florida, Illinois, and New York. So what I did was, I think there are just, I forget if it's 100 or 200 patients that live in the Chicago area. And what I did was, so each one of these letters is a patient, an A for ALND and S for SLNB. All right? So the blue line is the distance to the nearest hospital. The nearest hospital involved in this study. The red line is to the nearest high-volume hospital. And you can see there are, I forget how many there are. There's one here, one here, one here, one here. It looks like there are about 7 high-volume hospitals in the Chicago area. So stands to reason these hospitals all have the capability for SLNB. And you can't necessarily say that about the low-volume hospitals, right? They may or may not have that equipment. Actually, so our instrument is going to be the differential distance that the patient traveled. Okay? If they went to the nearest hospital, their differential distance is 0. If they went to a high-volume hospital, then it will be a positive distance. Okay? So, so it's a little hard to make these tables for a continuous instrument. So what I did was I just cut it off at 30 miles. Okay, and now I'm doing all 4 states. I'm not just doing Illinois. I just did Illinois so I could show you what it looked like. But now I'm doing all 4 states, and I'm just cutting it off at 30 miles. So if it's the differential distance is less than 30 miles, I'm saying they got SLNB, and if it's greater than 30 miles, they got ALND. Now look what happens. First of all, the difference in lymphedema drops dramatically, right? Although it's borderline significant now. But remember, this was 5.7, okay? Similarly with age, that's pretty close. NCI comorbidity index, I mean, it's almost dead on. But one thing that doesn't change, this is interesting because this is related to treatment. The association, or whatever the society is, you can see is still very, very significant. So what this did was, it evened out the things that were confounders, right? But it didn't change things that are related to the treatment. I mean, it changed them a little, but it didn't erase them, right? What would be the point of this if it erased the treatment effect, even if there was one? Then there'd be no point, right? All right, so we said the partial F test has to be greater than 10. In this case, it was 31.6. Okay, so we've got a strong instrument. That's interesting. So as we've seen, other people in the literature have done this too. this, the distance differential is very predictive. So our IVE here, minus 0.15, okay? So that means that SLMB is reducing lymphedema, but it's not significant, right? Womp womp. So no paper here. But just to go over these, so outcome is lymphedema, treatment ALMB versus SLMB, Z is the distance differential, and these are all the confounders that we adjusted.
But that partial F statistic is suggesting that that's an appropriate model.
Right, appropriate instrument. All right, so let's look at this. All right, so I didn't do this totally by hand because it gets to be kind of a pain to do this by hand every time, doing the two-stage least squares, because it gets a little bit finicky. So I just made a little macro that does this. But anyways, you put in the treatment, you put in the X's, you tell them which ones are class variables, you give it Y, which is lymphedema, and then you tell it what the instrument is. So I'm glossing over some of the details, but I want to show you the output. Oh, so you know what I forgot to show you? Well, we can come back to that later. Let's stick with this. All right, so the first stage. All right, this is just the first stage regression. All that really matters here is the partial F test. Okay? So here I just broke it out, 31.6. I think you can see that in the output above too. Yeah. So so SAS gives you the type 3 tests, which means it puts it at the end, which is the same as the partial F test. So you can see 31.6. Okay. So that's the stage 1 regression. Now we put t hat into the second stage. Let's see here. Okay. And that was the coefficient. So minus 0.15, p-value of 0.27. So it's leaning in the right direction, but it's not really strong evidence that it works. And then there's one issue with two-stage least squares, and that is, let me see, how does this work? Right, so when you're calculating the standard deviation, so the thing that I'm estimating, I'm calling hat, so t hat right here, okay? So there's one thing where to estimate the standard deviation, you're actually supposed to put in the real t instead of t hat. So remember, in this regression we put in t hat, but for the standard deviation part, you put in the real t. And if you've got a pretty good model, it doesn't change it much. So you can see the p-value was 0.27 with t hat, and when I put in the real t, it was 0.27 also. So if you get a really good model, you don't really have to worry about this step. But so while I'm in here, I just want to show you, we forgot to talk about using regression in propensity scores. So let's just show you this quickly. What time is it? Well, we don't have much time left, do we? Is that right? Did my watch jump ahead? All right, so let's just look at this quickly here. So I didn't try to think about this too hard. I just sort of used the same model I used to predict t, which isn't necessarily the right thing to predict y, but I added strata to it. So I'm predicting y, but I added strata, and you can see, actually these don't seem to change anything. Weird. So I don't know. I'm not sure. Theoretically, this is the right thing to do, but I kind of like the Cochran-Mental-Hensel test better in this situation. But I guess the two should agree. So if you get one that's wildly different than the other, then you know something's wrong. Who knows what it is, but... Okay, so now let's... All right, let's pick up where we left off. All right, so now let's talk about near-far matching. So this, the nice part about it is it works for binary outcomes even if it's near the boundary. Great, we're out of that problem. However, the matching strategy is, I'd say, way more complicated than propensity scores. They really have a, I mean, it sort of depends on what you're trying to accomplish. But for example, in this table, matching was difficult, right? Did everybody see that? So first they matched on regions, high versus low regions. Here, this is the way I wanted to show it to you. Okay, so let's look at this. So let's say this is the x-axis, and this is the z-axis. Okay? So what are we trying to accomplish here in near-far matching? So let's say we have, let's see. And the way I like to think about this, instead of just talking about one x, what I do is I think about it this way. Oops. Because x is multivariate, right? So I think about on this axis, I have the propensity score. This makes the matching easier, okay? So what you want to do here is you want to match patients that are very close on the x, but far apart on the z. Or wait, I'm doing it wrong. Let's see. Yeah, so these two patients are close on the x-axis and far apart on the z. And one more thing they do to make your life easier. What do they do? So let's say there's a patient here and a patient here, right? What do? They remove the middle. Right? So now you have two choices here. This choice doesn't count. You match to the furthest. That's the far match. The near match is this way, right? So this patient gets matched here, this patient gets matched here, and you ignore the middle. All right, so one of the problems, one of the difficulties it seems to me in reading this paper is just getting through all the notation. So instead of using their notation, which I didn't really like, I tried to make this whole talk with roughly the same notation. Z is always an instrument, T is always a treatment, et cetera, et cetera. So essentially what they've got here is, let's say they've got n subjects, and then they have a matched pair. So in the pair there's a 1 and a 2, okay? All right, so let's assume a binary treatment, or yes. We're assuming a binary treatment and a binary instrument. So we say ZI1 is discouraged. So I'm using j equals 1 for the discouraged. And for the encouraged, I have ZI2, and I'm using 2 for the encouraged. And it's ZI2 is 1, right? So that's these two, right? Now, what do we really want here? What we want is the counterfactual, right? We want this patient to be able to have the opposite treatment. So we want to also be able to see ZI1 encouraged, right? Or we want to see ZI2 discouraged, right? Well, that's what we've got here. These two are near matched and far matched. So this pair has, we're thinking about this pair as if, you know, they're a potential outcome pair. That make sense? You guys are way too quiet. Are you guys like this the whole semester, or is this my luck today? Okay. Oops. Oh, I must have bumped that. Sorry. Okay. So that's the idea. Okay. So so you have these pair of outcomes. Let's see. So this is like the. But now you don't know which one is which, right? So just because somebody's encouraged doesn't mean they get the treatment, right? And just because they're discouraged doesn't mean they did not get the treatment. So what you've got here is you've got a pair of outcomes for each IJ, right? So for each patient, and in each one of these pairs, there's two possible outcomes. There's I mean, how do I want to say this? Well, let's think of what the test is. The test is if I had not received the treatment and I had received the treatment, did I have the same outcome? Right? In that case, the treatment doesn't work, right? Well, we have something called the exclusion restriction. So the exclusion restriction means what does it mean? Right. So if both of these people got the same treatment, then they get the same outcome. Okay, so what this is saying here is, let's see. It's like this. This is why we want a strong instrument. If we have a very weak instrument, what can very easily happen is both can get the same treatment, both the discouraged and encouraged. And what happens then is there's no counterfactual, right? Because they got the same treatment. They both got the same treatment in the pair. What you want is a strong instrument so you can have what are called compliers. That means that given the encouragement, they got the treatment, and given the discouragement, they did not get it. So if you have a strong treatment, a strong instrument, then you have a good chance of testing this hypothesis. If you have a weak treatment, then you have a lot of these types of situations, and they sort of water you down. I think that's partly why we're eliminating the middles. We got to go to the extremes, a far match. And then finally, I just want to talk about the matching. So in matching, what you're doing is you're minimizing some function. So in this case, the way I think about it is you're minimizing the difference here of the propensity score, right? And you're actually maximizing this difference. See, so I have a -2 here. So I think that's another way to think about it. They didn't really address that directly. They got a little bit into the details of matching, which some of it was a little bit over my head. But I think you can do this in SAS. But it's not trivial doing the matching. Okay. So it's not for everybody.
Question. So for an objective function, like the way it looks to me that like the propensity score difference is being more important in terms of the objective, but obviously the functional form of the objective function. Is it usually you want to match more on the x-axis or more on the z-axis, or?
It's simultaneous is the way they.
So like, are you trying to do it basically like you're weighting them about equal in terms of importance?
Yeah.
Okay.
Yeah, I would say, yeah. Because the way I drew it is too easy, right? They're obvious what the matches are. I mean, you could have just a cloud here, and then there's trade-offs, right? Okay, so all right, so today you got a brief overview of causal inference for observational studies. Introduced you guys to propensity scores. Introduced two-stage least squares and near-far matching. I should just note that causal inference is evolving, and it is an important contributor to comparative effectiveness research. I mean, just a couple of years ago, near-far matching didn't exist, so it's a constantly evolving field, and it's necessary. We can't easily do comparative effectiveness research without it. So if you really want to see this again, which I doubt, you'll find this lecture will soon be online, and the slides will be online also. Okay? And this will be, so you can go on the Biostat website and you'll see these links. And one of the reasons I'm putting it online is because there's a lot of references that you may find of use if you ever have to actually do this. So I've got all the references at the end. Okay, so we have like 5 minutes for questions.
I'm gonna go back to the website page again.
Oh, okay.
Yeah. Thanks.
Yeah, so we have our own YouTube channel where this will be going, so we're going to try to put it up there. We have a lot of stuff up there already. Nothing recent though, so this will be fun to put up something new up. All right, anything else? Any questions about the papers? Like I didn't really get a chance to get into the papers as much as I thought I was going to, but I mean, I wanted to assign more papers, but I felt like I think these two were very representative. But obviously, they're just two papers. There's lots of stuff lots more stuff that you could you wouldn't waste your time reading if you're actually going to do this. Okay. All right, let's wrap it up then.
Thank you.
You're welcome.